All right, welcome to lecture 3. Today we're going to be talking about energy, heat, and temperature. And I think it's a pretty cool lesson. I think it can apply to a lot of the stuff that you deal with on a daily basis. We'll kind of be talking about a little bit of food chemistry, and hopefully throughout the course we can make some cool connections so that, you know, you're learning how to solve problems, but you're also learning some cool connections to chemistry in real life. So I'll go ahead and start with the PowerPoint here. Let me pull it up. Okay. All right, so energy, heat, and temperature is what we're talking about. So just to kick it off, go ahead and pause the video and do this little quiz. This will mostly just kind of be guessing at this point. Because we haven't talked about this yet, but just kind of an interesting idea here. All right, so in this problem, we talked about how a Snickers candy bar has 250 calories in it. A calorie in chemistry, and I guess a calorie in general, is just a unit of energy. A lot of times people who haven't taken chemistry view calories just like, right, it's like this has so many calories, it's bad for you or good for you or something like that. But we're going to talk about what a calorie really is and what it means when you see it on food. So like we say here, a calorie is a unit of energy, and energy is required to heat things up. So in the case of our body, right, a calorie is a unit of energy, and so we get energy from food. So foods that have more calories give us more energy, and that's kind of what it boils down to. So, and then I guess if you want to think about, weight loss or weight gain, essentially, if you have so many calories and you end up not burning all those calories in one day, you have leftover calories that can turn into excess weight on your body. Or if you're burning more calories than you're eating, then you're going to be losing weight. And, weight loss is pretty much summed up that way simply. There's a lot more things that are going on, but essentially that is how you would gain weight or lose weight. Okay, so the question says, if we could take all the energy in a Snickers bar and use it to heat water from 0 to 100 degrees Celsius, how much water do you think we would be able to heat up? So this might sound a little weird, again, if you don't have a lot of exposure to chemistry and calories, but essentially calorie is just energy, right? So we can use energy to heat something up. And so in this case, say we took all the energy that's stored in that Snickers bar and heated water from 0 to 100, how much water could we heat up? And the answer is actually 2.5 liters, right? So think of like a 2-liter soda. That's a little bit more than that is how much water you'd be able to heat up with just the energy from a Snickers bar. So that's quite a lot of energy, and we'll talk about that a little bit more throughout this PowerPoint. Okay. So there's two kind of energies that we'll talk about here. So potential energy generally just depends on position. So if you've taken physics, a lot of times they put a ball at like a top of a hill and they say this ball contains a certain amount of potential energy, right? And then the equation they usually give you is like mass times gravity times height. And then kinetic energy depends on the speed. So then as that ball starts to move down the hill, it loses potential energy because the height isn't as high. But as it picks up speed, it's gaining kinetic energy. So that potential energy is converted into kinetic energy. And so just kind of talk about these things to highlight the idea that you can convert potential energy into kinetic energy. And so energy in general can be converted between different forms of energy. It's easier to illustrate with like a physics principle because physics, you can generally see these things happening, right? In chemistry, you can't really see the molecules and what's going on at that level with your eyes. So it's a little easier to think about it in terms of physics. But really all I wanted you to get from this slide is just that like energy can be converted, okay? And so again, this illustration at the bottom shows a roller coaster example. So in this first position, there's all potential energy, zero kinetic energy if it's not moved. Once it starts moving, that potential energy is converted into kinetic energy. It's fastest when it's at the bottom, and then it can move, be converted back and forth as the roller coaster goes along. So in chemistry, potential energy comes from the positive and negative charges in molecules that are attracting and repelling each other. And then kinetic energy comes from the motion and vibration of the molecules and the atoms that are within the molecules. So for right now, don't worry too much about these definitions. Again, just kind of want to illustrate this principle that energy can change from one form to another. Okay. So let's see if this video works on the Zoom screen capture here. But this is me in Idaho. I love Idaho. It's one of the greatest states in the world. And we're doing tannerite. So this is a mixture of two molecules. And as it sits, it just sits in a container, a plastic container that's sealed. And while it's sitting there, there's lots of potential energy, right? And then what we do is, or what we did in this video, you shoot it. And if you have a bullet that's a wide enough caliber and is going at a high enough speed, all that potential energy is then converted into kinetic energy, and you see that in the form of an explosion. So I can't recommend you try this at home, but I just wanted to show you kind of this video of how it works. So let's see if this works. Yeah. Anyway, pretty cool principle. Again, it's just kind of showing that energy can be converted from potential to kinetic. So anyway, and in this case, the potential energy isn't dealing with like the height of something like you would think about in physics, but you have energy that's stored within the bonds of the molecules, and that event of the bullet going through converts that potential chemical energy into kinetic energy and also some thermal energy and stuff like that in this case. All right. So in chemistry, think of energy and heat as very related, okay? Even sometimes you might hear these terms like used interchangeably. But heat is really related to the total kinetic energy from the thermal motion of the molecules in the atoms, right? So the faster the molecules and atoms are moving, the more heat is in that molecule, okay? So that's kind of how you can think about it, right? And when you add heat to something, what you're really doing is speeding up the motion of the molecules and atoms. Heat we represent with the variable Q. So that's what you'll see in different equations and stuff that relate to heat. And then the units that you'll see are either joules, represented by a J, or calories, represented just by CAL, okay? And then there's a conversion here, like we talked about conversion factors in the last lecture. Okay, we can convert easily between calories and joules because 1 calorie is equal to 4.184 joules. So just as a review, if you're going to be using this equality in a conversion, right, you could put 1 calorie over 4.184 joules, or you could do 4.184 joules over 1 calorie, okay? All right. So, like we talked about, when you add heat to an object, what's happening, right? We say it gets hotter. What does that really mean? That just means that like the molecules and atoms are moving faster. And so when you touch it, that feeling of them moving faster is feeling of heat, right? And the temperature goes up. Temperature is a measure of how fast molecules and atoms are moving, right? It's a measure of the kinetic energy that's involved. Okay. So then we can consider questions like this. If we add 100 calories of heat to water, how much does the temperature increase? Okay. So let's say you're using a smaller Snickers bar that has 100 calories, and we're going to talk about food calories versus the calories you see right here, but just for the simplicity of the example, right? Snickers bar has 100 calories. If you burn it, how much is that going to make the container of water go up? Well, there's a couple variables we need to think about here. It first depends on how much water you have, right? If you have a large amount of water, it's going to take a lot more heat to raise that much amount of water by the same amount of temperature as a smaller container of water. So you could try this at home, right? If you boil 1 cup of water on the stove versus 10 cups of water and time it, you'll find that it takes longer to boil 10 cups of water, but you probably have experienced already or maybe seems intuitive to you. So we need a way to connect the temperature change, heat, and the amount of water. So what we have is something called specific heat. And the definition of specific heat is the amount of energy it takes to raise 1 gram of a substance by 1 degree Celsius. And so you'll see that in the units here, okay? So the units for specific heat are calories per gram degree Celsius, or sometimes you see it as joules per gram degree Celsius. And again, this is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius, okay? And that's represented in these units. The amount of energy, a calorie, required to raise 1 gram, right? You could write this as 1 gram times 1 degree Celsius. The amount of energy in calories required to raise 1 gram of a substance by 1 degree Celsius. Okay, so you can kind of see that in the units there. So I should say, or you'll see this as joules over grams degrees Celsius, okay? Okay. So calories we can represent as heat, right? Because calorie is just a unit of heat or a unit of energy. Grams is whatever the mass is, and then degrees Celsius is going to represent the change in temperature, okay? So when you see this delta T represents temperature change. Whenever you see delta, that means the change in something. And so how you calculate delta T is you take the final temperature minus the initial temperature. Okay. All right. That's true for any delta, whatever you see, right? If it's delta grams, it's going to be the final grams minus the initial grams. But usually we just, for the most part, see it with delta T, and it's the final temperature minus the initial temperature, okay? So then you get this equation where C, the specific heat, which is just a variable that we've created, okay, is equal to calories over grams degrees Celsius, or Q over M delta T, okay? And again, this is just a variable that we created to connect these three. So just by definition, it was come up with heat over mass delta T. We're going to call it specific heat, okay? If you rearrange this equation, right, you could just multiply the mass in delta T over with the C, and you get Q equals M, which is the mass, C, which is the specific heat, and delta T, which is the change in temperature. You'll often hear me just reference Q equals MCAT because it's easier to say and it helps you memorize the equation better, right? So Q, the heat, equals MCAT, mass times specific heat times the change in temperature, or delta T. So this is the equation that you're going to use for all of these heat and calorimetry problems, and we're going to talk about that coming up here. Okay, so here's an example problem where we can use that equation right here, okay? Pull this up, okay. So if we add 250 calories of heat to 2 liters of water, how much does the temperature increase? So now we know enough to be able to solve this problem. So Q equals MCAT. So Q is going to be the amount of heat, right? And in this case, it's given to us 250 calories, okay? So 250 calories is equal to, we need the mass, and we're not given the mass in the problem here, okay? We need C, which is the specific heat, which we are given, that's right here, okay? So this is going to be mass, so M, let's put this underneath, Q equals M times C, which is 1.00 calories per gram degree Celsius, okay, times delta T. And it says, how much does the temperature increase? So that means that delta T is what we're trying to solve for, right? Because the question's asking for it. You can't solve an equation unless you have at least 3 of the unknowns. And right now we have Q, we have C, we're solving for delta T, right? So we're going to need the mass in order to solve this problem. So we can look at what other information that we have given. So if you remember, this Greek symbol here, rho, refers to density, okay? And we have the volume of water. And we can convert volume to mass using the density from the last lecture. So let's say we have 2.0 liters of water, okay? We can convert liters to milliliters. We have 1 liter is equal to 1,000 milliliters, okay? And then we can convert milliliters to grams using the density. So the density here is just 1. So 1 gram for every 1 milliliter, okay? So if you run through this math, right, we should get, sorry, I was running out of room, but you get 2 times 1,000 times 1. So that'd be 2,000. Okay, your liters cancel out. Oh, sorry, this should be flipped. This would be milliliters on the bottom and grams on the top. Sorry, milliliters cancel out and you're left with grams. Okay, so 2,000 grams, okay, of water is what you have. And then if we look at significant figures here, we have 2 sig figs in this number. This is the exact conversion. And then the density has 3 sig figs. So our answer needs to have 2 significant figures, okay? So we really have, if we wrote this as 2 significant figures, it would be 2.0 times 10 to the power of 3 grams, okay? And that has 2 sig figs. All right, so our mass is 2.0 times 10 to the power of 3, okay? Grams. Awesome. Okay. So now we should be able to do this problem, right? So if you just do a little algebra, you have 250 calories divided by 2.0 times 10 to the third grams times 1.00 calories per gram degree Celsius, okay? And this is going to equal delta T, okay? So you can put this into your calculator and solve it. And then also notice that this number here, sorry, this actually should have a decimal, right? Because that's how it's given to us in the problem here. And that makes a big difference. That means this number has 3 significant figures. This number has 2 significant figures. This number has 3 significant figures. So our answer is going to be limited to 2 significant figures, okay? So let me just back up and plow through it with the more legible writing here. Okay, so we have, in this case, instead of writing it out in the Q equals MCAT form and then doing the algebra, you could just rearrange the equation, right, to give you delta T equals Q over MC, because we know we're solving for delta T. And then you just plug in the numbers. So we have 250 calories, right? That's Q. Our mass, we can do the conversion right in here. So our mass gets converted to, where are we at here? Sorry. Okay. Let's see, C, this is C, okay, that's your specific heat. And then the mass that's on the bottom here, we need to convert eventually over to grams using the density here. So sorry, it's a little hard to see using this approach, but hopefully the approach that I drew out, it was a little easier to see how to do it, right? Okay. You can see how units crossing out gives you temperature, which is what you're looking for. So again, going back to last lecture, if you can really just analyze these units, cross things out, and get to your answer, it's going to be super helpful. But another way to look at it, right, and we said there's 2 significant figures in the answer, which is what we have here. So you can kind of see that there's a lot of different approaches. Sometimes my approach will be different than what I have here in the PowerPoint slide. Just to show you 2 different ways. I approach them all about the same. So you kind of find out what works good for you as you're doing the homework and stuff like that. All right. So think about this. So at that first question we talked about in this PowerPoint, we said 250 calories would heat 2.5 liters up 100 degrees Celsius. And now we're saying 250 calories would heat 2 liters of water only by 0.13 degrees Celsius. So you might think that doesn't make sense. Well, now we're going to talk about a common confusion that happens, okay? So in the beginning we said calories and I had a capital C. Okay, so there's calories with a capital C and then there's calories with a lowercase c. So the food industry uses calories with a big C, and that is actually equal to 1 kcal of a smaller c. So the actual calorie is with a small c. And the thing is, like, it would look really bad to say a Snickers bar has 250,000 calories, right? Because it really does have 250,000 calories with a small c. And so instead they just made the c bigger and said, okay, we'll call the big C equal to 1,000 calories of the small c. So now a Snickers bar only has 250 calories with a big C. Anyway, hopefully that's not too confusing, but just remember, if you see a big C, it's actually equal to 1,000 calories with a small c. These are sometimes just called food calories or kcals, right? So 1,000 calories would be equal to 1 kilocalorie. And if you've been in a different country, a lot of times the label actually uses kcals instead of calories. So a Snickers bar would say 250 kcals if you were in, like, I don't know, Brazil. I served a mission in Brazil, and so down there, all the food was reported in kcals. So that kind of makes sense. But look for the capitalization on the C, and don't let that confuse you too much. So again, here a 250 calorie Snickers bar actually contains 250,000 calories as little c calories. Okay. All right. Demo, let's skip over. So we're not in class, unfortunately. Okay. Go ahead and pause the video and try and work through this problem on your own and see how you do. All right. Let's answer it. So the question says we have 500 milliliters of water at 25 degrees Celsius, and we want to bring it to a boil. How much heat do we need to add? So the question says how much heat, right? Meaning we're going to be solving for Q, because Q equals heat. And so really we just need three things. We need the mass, we need the specific heat, and we need delta T, okay? All right. So first let's look for the mass. So we are given the amount of water in volume. So again, this time we're going to have to convert the volume to grams. And so we can take 500 milliliters of water and we can convert it into grams of water using rho, or the density here. Okay, so we can say 1 milliliter is equal to 1.00 grams of water, and this is milliliters of water. Okay, so your units, milliliters, cancel out and you're left with grams of water, and this is 500 with a decimal. Okay, so if you do this calculation, right, 500 times 1 would be 500, right? And then if that'd be 500 grams of water. And here we have three significant figures in this number. We don't take into account because that's just an exact number here. So our answer needs to have three significant figures. So it's 500 grams. So you'll probably quickly recognize that when you're dealing with water, because the density is equal to 1, the amount of milliliters in grams are actually equal, right? Because it's 1 gram for every 1 milliliter is the density of water. Okay, so we have the mass now, right? Check. So now we need specific heat. Well, that's just given to us right here. So we have that one. And then we need delta T, right? So if you remember, delta T equals the final temperature minus the initial temperature, okay? So delta T is going to equal whatever our final temperature is. And the question doesn't explicitly say what the final temperature is, but it says you want to bring it to a boil, right? And water boils at 100 degrees Celsius. So I'm not going to expect you to know boiling points and melting points for everything, but you should know for water that water freezes or melts. It transitions between solid and liquid at 0 degrees Celsius, and then it boils at 100 degrees Celsius, right? So it transitions from a liquid to a gas at 100 degrees Celsius. So water, you should know. All the other ones you don't have to worry about memorizing them. Okay, so the final temperature, if we're boiling the water, is going to be 100 degrees Celsius minus the initial temperature, which is going to be this right here, 25.0 degrees Celsius, right? And so our delta T is going to be 75.0 degrees Celsius. And for the sig figs here, because this is a defined value and it doesn't really give us sig figs, I'm just going to treat this as an exact number and not worry about the sig figs here. Here this is measured, right? Because we're measuring that it starts at 25.0 degrees Celsius. And so since this is reported to the tenths place, 1 decimal point, we're going to have our answer reported to 1 decimal point as well. All right, so now we have the delta T, and we can run through the equation, right? So Q is going to equal the mass, which is 500 grams, times the specific heat, which is 1.00 calories per gram degrees Celsius, times delta T, which is, oh, sorry, that should be a multiplication, times 75.0 degrees Celsius. Put this in your calculator. All three of these numbers have 3 sig figs, so your answer is going to have 3 sig figs, right? Okay, I'm just going to run through it on here. This is like we did, we calculated the mass first by multiplying the volume times the density. You can cross out your units and get the mass of the water that you have. Delta T is final minus initial. 100 degrees Celsius minus 25 degrees Celsius gives you 75 degrees Celsius. And then it's just plugging in, you have the mass, the specific heat, and delta T gives you your answer. And to 3 significant figures, the answer is D here, okay? All right. All right, another practice question that we're gonna try. So you go ahead and pause the video again and try doing this one. All right, coming back here. So the question says you want to determine the specific heat of a metal. So if we're doing specific heat, right, that means we're going to be solving for C, okay? You find that 24.8 grams of metal, so that's your mass. So you could start writing these out as you read the problem. Sometimes that helps, right? Our mass equals 24.8 grams, okay? Absorbs 65.7 calories of energy, okay? So that means our Q, which is our heat, right, is going to be 65.7 calories of energy. And the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius. So again, delta T equals final minus initial, and the final temperature is 24.5 degrees Celsius. Minus the initial temperature, which is 20.2 degrees Celsius, okay? And so that's going to give you a difference of 4.3 degrees Celsius, right? Accurate to the 10th, to 1 decimal point, or 1 decimal place, because we're doing subtraction here. So even though there's 3 sig figs in each of these numbers, our answer only has 2 sig figs because when we're doing subtraction, we just go to the smallest decimal place. And in these cases, both numbers have 1 decimal place, so our answer has 1 decimal place. Okay, and then it asks, well, the question just says, what is the correct number of sig figs, right? But we now have the mass, we have Q, and we have delta T, so we can go ahead and solve this equation. Okay, and you're going to be doing, if we do the algebra beforehand and just make up an equation for C, right, we can do Q is going to equal Q over M times delta T is going to equal C. So Q has 3 sig figs, the mass has 3 sig figs, and delta T has 2 sig figs. So our answer is going to have 2 sig figs, which means without doing the calculations, we can just say our answer is D. But if you did run through this, you know, you'd probably find that as well. So let me walk through it here, rearrange the equation, and then put all the numbers on there. And those 2 sig figs will limit your answer to D, okay? All right. Okay, so this brings us to calorimetry. So calorimetry is kind of going backwards a little bit, but this is how you find out how many calories are in a food, right? So maybe at this point you've wondered, how do you even know that a Snickers bar has 250 calories, right? Essentially what's happening is, so this is an image of a calorimeter, okay? So you have your food sample right here, okay? So this is the food sample. So imagine you have a Snickers bar in this calorimeter, and then you light it on fire, okay? Well, the amount of energy that's released, okay, it's going to release energy in the form of heat, right? When you burn something, it's hot, okay? And calories are just a measure of energy or a measure of heat. So that heat's going to come out of the Snickers bar and it's going to go into the water that surrounds, right? This is in a chamber of water, okay? And then you have a thermometer that's sitting here in the calorimeter. So in order to know, let's say you're trying to find out the calories in a Snickers bar, right? Take your equation, Q equals MCAT, okay? Oops, Q equals MCAT, okay? And we're solving for Q, right? Because we want to know how many calories are in a Snickers bar. Well, it's hard to do on the Snickers bar itself. But if we say the amount of energy released, so Q released by the Snickers bar, sorry, this is such bad handwriting. This pen is taking a little to get used to. Okay, the amount of energy released by the Snickers bar, it's all going to go out and go into the water. So that means the amount of energy released by the Snickers bar is the amount of energy absorbed, okay, by the water. So although we can't really directly calculate the calories of the Snickers bar because we don't know the specific heat of the Snickers bar or really the delta T in the Snickers bar, we can calculate the amount of energy in the Snickers bar by calculating the amount of energy that goes into the water in the surroundings. So for the water, right, let's say we're just trying to figure out the Q absorbed, which is the amount of energy absorbed by the water, okay? That means all we need to know is the mass of the water, which you could measure, right? You know what the volume of this is. So that's a check mark. We know what the mass is. Specific heat of water is 1 calorie per gram degree Celsius. We already know that. And then the delta T, we can measure the temperature of the water before the Snickers bar is burnt and after it's burnt. And since we know the final and the initial temperature of the water, we can figure out delta T. You can use those to calculate the amount of energy absorbed by the water, which is equal to the amount of energy released by the Snickers bar, and you then have the amount of energy in a Snickers bar, okay? So that's the process, okay? Okay, so shown here, heat released by the sample is equal to the heat absorbed by the water. Again, we know we know M, we know C, and we know delta T for water, so we can solve for Q. Okay. Awesome. There's just some more information there. Okay, so in real life, do they burn a Snickers bar? Not usually, right? So a Snickers bar they know how many peanuts, I think there's peanuts in there, how much peanuts are in there, they know how much chocolate's in there, right? Or even if you break it down further, they would know how much like butter's in there or whatever. And so they can do these calorimetry experiments on very basic ingredients and then come up with values that way. And then just by using the recipe for a Snickers bar or whatever it is, you can calculate the calories without actually having to stick a Snickers bar or whatever food is made into a calorimeter, okay? All right, so here's an example calorimetry problem that you would see. So we have 4 grams of oil burned in a calorimeter that contains 2 liters of water. The temperature of the water rose from 25 degrees Celsius to 43 degrees Celsius. What is the energy value of the oil, right? So although the question is asking for the energy value of the oil, what we really want to do is just calculate how much energy is absorbed by the water, okay? Because that is equal to the amount of energy given off by the oil. So the Q for the water, H2O, okay, is going to equal the mass of the water, which we need to find out. We need the specific heat of water, which is 1.0 calories per gram degree Celsius, okay? And then we need the delta T, right? Which is going to be the final temperature, so 43.0 degrees Celsius minus the initial temperature, which is 25 degrees Celsius. Sorry, 25.0 degrees Celsius. Okay. So what we really need now is the mass of the water, right? And then we can take the volume of water and convert it to mass using the density. Remember, the density of water is 1.00 grams per milliliter, right? It's just one. So I won't draw it all out, but you can come out with the mass of the water using the density and doing that conversion. And then you can solve for the amount of energy absorbed by the water, which equals the energy value of the oil, okay? So let me walk through that and make sure I covered everything. Okay, so again, this whole quantity here is just converting volume into grams using the density to get the mass of the water. Multiply it by C, which is the specific heat, and then by delta T, and it's 36 kcals that are released, okay? Energy values, it kind of depends what the question's asking for, but if the answer choices are all in kcals per gram, then you have one final step, right? Because this only gives you an answer in kcals, okay? So if you cross out all the units, you're left with calories, which is 36,000 calories, which if you then convert it to kcals would be 36 kcals. The energy value of the oil, so if the question is asking how many kcals per gram, then you would actually take your kcals and divide by the grams of oil, which is just given here at the first part of the problem. And then you know it's 9 kcals per gram is the energy value. So kind of depends what the question is asking. If the question just asked how much energy is released by the oil, then you would just leave it in calories or kcals. Depends what your answer choices are. But if it's the energy value and the answer choices all have units of kcals per gram, you need to do the extra step so that your answer is in terms of kcals per gram. So a lot of times the answer choices will kind of help you understand where you need to be, right? Okay. This is a calorimetry test on a peanut. Anyway, generally in class, I'd burn a peanut under a can of water and we record the temperature and then we can figure out how many calories are in a peanut. So there's probably YouTube videos on that. If you're really interested in looking it up, you could just search calorimetry with a peanut or soda can or something. And there's probably some videos of people doing that. Okay, so this quiz here, 2.3 grams of butter are placed in a calorimeter with 1900 grams of water at 17 degrees Celsius. Butter is burned and the water temperature rises. What is the energy content of the butter in calories per gram? Okay, so again, this question tells you what units you need to be in, so it kind of helps you direct where you need to take this question. So I think what you can do for this question and other questions is pause right now if you want to try and do it. If you get stuck, hit play, follow along for a little bit while I'm working through it, pause again and try and figure out the rest. So you can get little hints along the way, maybe that way. Anyway, or if you're totally lost, you might need to watch it and then just practice this stuff later. So I'm going to go ahead and start working through this problem. So we want to know what the energy content of the butter is. So it's asking for the answer in calories with a big C, okay, so it's kcals per gram. The gram is given to us, right? We know we have 2.3 grams of butter. So that part we don't have to really solve. But what we do need to figure out how many calories are in 2.3 grams of butter, right? So again, this is that calorimetry. So if you go back to that visualization, the amount of energy or calories released by burning the butter is going to be the same as the amount of energy that enters the water. So I'm going to look for the Q of water, right? Or the heat absorbed. Okay, so I need the mass of the water. Oh, and this already gives it to me in grams, so I don't have to convert from liters to grams this time. So my mass is 1900 grams. Okay, specific heat of water, we know it's 1.00 calories per gram degrees Celsius. Okay, now we just need delta T. So the water temperature rises to 28 degrees, and it started at 17 degrees and goes to 28, right? So our final temperature is 28 degrees Celsius minus 17 degrees Celsius, okay? So that would be, if you do that, that's going to be 11 degrees Celsius, right? So if I put this into my calculator, I'm going to get 1900 times 1 times 11, right? So let me do this real quick. 1900 times 1 times 11. So I get 20,900 calories, okay? Now the question's asking for calories with a big C. And so if you remember from the previous slide, 1 calorie, oh sorry, not that, 1,000 calories with a little c is equal to 1 calorie with a big C. So now I can say the heat of water is equal to 20,900 calories. And then if I convert this, I can say 1,000 calories is equal to 1 food calorie, or calorie with a big C. So I do that, and then I should get 20.9 calories with a big C, right? And at this point, I'll probably go ahead and take this to the correct number of significant figures, right? This was actually 11 degrees Celsius when we did the subtraction, so that's 2 significant figures, 3 significant figures, 2. So our answer needs to have 2 significant figures. So our answer would be 21 big cals, right? So we're not done yet. So we figured this part out. Now we just need to divide by the grams. Okay, so we're going to say 21 calories over 2.3 grams. Okay, and that will get us, 21 divided by 2.3. It's going to get us to 9.1304, blah, blah, blah. It goes on and on, okay? And then we need to round that to 2 significant figures because these 2 numbers both have 2 significant figures. So that would be 9.1 calories per gram. So that makes, oh, not C, I mean B. That makes B the correct answer. Okay. This is just going through it with the more legible handwriting here. B is your correct answer, okay? So just the last note here. I'm not gonna really spend a lot of time talking about this, but just things you ought to know is converting from Fahrenheit and Celsius. I'll have the equations to do this on the equation sheet, or converting from Celsius to Kelvin, which is something we'll use a little bit later. So it's not that you need to like memorize the formula, but just know how to do it using the formula. And then remember that the Q equals MCAT formula that we use needs to be in Celsius, right? Sometimes you just have to really check your units. For example, this problem we just did, it it gave the temperature values in Celsius, right? But there's a chance that a problem could give these to you in Fahrenheit, require you to convert from Celsius to Fahrenheit, or sorry, convert from Fahrenheit into Celsius before you actually do the problem. So always just be aware of units. And again, right now we're going to use a lot of Celsius. Kelvin is a unit that we'll use later when we talk about gases. So I think that's it. Oh, convert from joules to calories. We talked about that conversion factor as well. So, all right, I think that's all. So hopefully that lecture was helpful, and hopefully these are working pretty well. If you have any suggestions for how they can be better, I'm totally up to it. I'm used to just teaching off of a chalkboard, and this pen is kind of hard for me to write legibly. But hopefully they're working. Let me know what you think. You send me an email, or you can comment on the YouTube video. I'm totally open to adjusting how I do things if people think there's a better way. So hopefully this works out well for you, and we'll see you next time.